My name is Abhishek. Welcome to my YouTube channel. This is a playlist for interview questions and problem solving sessions. We will be taking the problem statement and try to see the different approaches to solve that problem. And also we will implement the discussed solution in Python programming. So in the previous session, we have seen how to find the position of an element when the array is unsorted. Now let's read the problem statement. Given a sorted list L of n elements with values or records L0 to Ln-1 and target value t, find the target t in L. So you have to find the position of the target element in this list L. If you see the problem statement, so the array is sorted. So when the array is unsorted, you have to apply the linear search. But when the array is sorted, you can see for a better approach. So the first thing that comes to your mind when the array is sorted is binary search. So binary search can be applied on the sorted list, and it cannot be applied for it cannot be applicable for when the array is unsorted. So binary search is also called as half interval search or logarithmic search because the search time taken to search for an element is half of the size of the array. So that's why it's called as half interval search, and it's better than linear search. So let's see the working of binary search. So let's take an example. So this is an example array of size 9, and these are the data elements and indices. So what binary search does is it will find the middle element for this array. So what is the middle element for this array? It is 15, and let's assume we are searching for the value 22 in this array. So what it does, it will compare this middle element with the target. So is 15 is equal to 22? No, right? So if it is equal, let's assume it is equal. So if this match is equal, it will return the middle as the position. So it will say I have found the element in this position. So that is mid. So if it is not equal, so it is now in this case it is not equal, right? So what it does, it will split this entire array into two halves. So it will split it to left and right. So what it does in the next iteration, it will compare this. Is 15 is greater than 22? No, right? So it means that 22 is definitely will be in the right side because the array is sorted. So if the target element is less, it will be definitely in the left side. So in the next iteration, what it does, it will ignore this left part and only search the elements in this right array. So now in the next iteration, it will similarly find the middle element for this subarray, which is right, and try to compare the target element. And if it is equal, it will return the mid as the position. If it is not equal, it will continue to split this right subarray into two halves and apply the same. Now let's draft a pseudocode according to the working of binary search. So we will be setting the left index to start of the array and right index to end of the array. So that is L is equal to 0 and R is equal to size. So we will check is left index is greater than right index. So what it means, if the left index has searched this entire array and moved out of this right index, that means we have searched the entire array and we have not found any matching element in the array. So the array size has ended, we have to terminate the program. So in that case, we will return search is unsuccessful and terminate the program. So if not, we will calculate the middle. So how do we calculate this middle index? We can calculate it by left index plus right index divided by 2. So this will give the exact mid position of this array, and we will compare this target element with the array element, that is the current mid. So if it is equal, so if the target and this mid element are equal, it will return the index as mid, and it will say we have found the position of the target element, and mid is the position of the target element. So if not, we have to split this entire array into two halves. So what is the condition to split? So if array of m, that is current middle element, is it less than target? So in this case, is 15 is less than the target 22? True, right? It means the array will be in the right index. We have to move the left index to here. So that is what we are doing here. Left is equal to mid plus 1. If not, is this 15 is less than target element? So if the target element lies in this array, let's assume that we are searching for 6. Is this target element, which is 15, is it greater than 6? True, right? It means it will be in this left half. So in this case, we have to move this right index to here. So we are moving the right index to middle minus 1. So let's see the code snippet for the same. So we are using the same condition, which is left index is it less than right index, and try to calculate the middle index. So you need not to use the same condition. You can use left index plus right index divided by 2, and we will compare the current middle element with the target. If it is equal, it will return the middle index. If it is not, we have to split the array. To split the array, this is the condition. So we have written the same condition here. Is array of mid is less than target, it means we have to move the left index to middle. Otherwise, we have to move the right index to middle. So that we will split, we will either ignore left half or right half for the next iteration. So let's take an example and try to see is this code that we have written works for the binary search for finding an element. So this is an example. We have an array of size 10 elements in this array, and we can see the index starts at 0 and ends at 9. So we are setting the initially we are setting the left index to beginning and right index to end of the array. So how do we calculate this middle element from this array? So middle is equal to left plus right divided by 2, which is 0 plus 9, 0 plus 9 divided by 2, which is equal to 4.5. As array indices are integers, right? We can't use the decimal representation, right? So that's why we are taking the floor value, which is 4.5's floor value is 4. So we will be taking the floor value. Now we have found array of 4 is the middle element. So what is there in array of 4? 15. So we will check this condition. Is current middle element is equal to target. So is 15 is equal to 22? False, right? This will not execute the if block. This will not return index. Now what it has to do if it is false, it has to split the array into two halves. So how do we split it? So we will compare this. Is 15 is less than 22? Is this 15 is less than 22? True, right? It means the target element will be in the right side of the array. So we will ignore this entire left part and move this left index to here. So we can see in the second iteration the left index is at here. So we can ignore this part. So let's see in the next iteration, as we have not we have not reached the size of the array. So then in the next iteration, what is the middle element for this subarray? So we can calculate using 5 plus 9 divided by 2, which is equal to 7. So is array of 7, what is array of 7? 50. Is 50 is equal to 22? False, right? So now we have to compare the condition. So what is the condition? Is array of bit is 50 is less than 22, which is false. So this will not execute this statement. It will go to else block and move the right index to middle. So what it does is in the next iteration it will move this right index to middle minus 1. What is a middle? Middle is 7, right? So it will move to 6. So it will move the right index to 6. You can see in the next iteration the right is 6. Now let's compute the middle index. Middle index can be calculated by left plus right divided by 2. 5 plus 6 divided by 2 is equal to 5. So is array of 5, what is array of 5? 22. Is 22 is equal to 22? Yes, it is true. So this condition is true. Now the program will return the middle index. What is there in the middle index? 5. So we can say we have found the element 22 in this array at position 5. So that's about the tracing. Now let's get into the implementation part. So I have defined a function binary search which accepts array, size and target. Array is list, size is integer which is the total number of elements in the array, and target is integer that we are finding in this list. So it returns the position index, like the position of the target element, if the search is successful. Otherwise, let's say we have reached the end of the array and we have not found the target. So in that case, it will return -1. It means the search is unsuccessful. So let's get started with assigning the left to 0 and right to size. So we will be setting the left index to 0 and right to size of the array. So let's take middle as none initially. So what is the condition for exiting? So the array size has to exit. So we will check is left is less than or equal to right. So if the condition satisfied, we have to compute the middle element index. So we can compute using mid is equal to left plus right divided by 2. So this will give the floor value. Now what we have to do, we have to compare current middle element with the target. So let's compare. If array of mid is it equal to target that we are finding, if it is equal, we will return the mid as the position. We will say we have found this target element in the position mid. So otherwise what we have to do, split the array into two half, so that in the next iteration we will ignore one part of the array. So what is the condition that we have written? If array of mid is less than target element, that means the target will be in the right half. So you have to move the left index to middle. So what you will do, left is equal to mid plus 1. So otherwise, so what you will do, you will move right index to middle, so that you will ignore the right half and only concentrate on the left half. So what is the condition? Mid minus 1. So let's say the array size exceeded. So what you have to return? You have to return -1, saying that the search is unsuccessful. So this is the iterative approach for binary search. So let's run this. So I have already written the driving script. So this is the array, and to find the size of the array, we can use this len function. This will give the size of this array. So we will be trying to perform binary search until user enters yes, and we will get the target from the user itself by using this input function and call this function that we have written, binary search. So we will call the function with array size and the target from user. So if the position is -1, it means the search is unsuccessful, we could not find the target. If it is equal, we can find the target in this position. So this will return the index of the middle element. So we will be printing that here. So let's run the snippet. Yes, I want to perform binary search. Enter the element that I want to search. So let's enter 11. You can see the search is successful. We have found the element 11 element found in position 4. 1 2 3 4. Yes, it is in the 4th position. So let's search for another element which is in the right half. This is 72. Let's see. Yeah, search is successful and 72 is found in position 9. So let's search for an element which is not there in this array. So what shall I give? I'll give 13. So yes, I want to perform binary search. 13 I want to search. You can see the search is unsuccessful. 13 element could not be found in the array. We have seen the iterative version of binary search. Now let's see how we can do the same operation using recursive operations like a recursive function call. So I have defined the function recursive binary search. It accepts array size, target, and left index and right index. So similarly, as we did in the recursive approach, we were using the while loop to iterate through it, right? So in this case, we will call the same function again and again until we have found this target element. So let's see the condition. So we will check is the size of the array exceeded. If it is exceeded, we will return -1. If it is not, we will similarly as we did in the iterative approach, we will compute this middle element and try to compare the current middle with the target. So if it is equal, we will return the position. If not, we have to split the array, right? So previously what we were doing, we were just updating the left index and right index by middle +1 and middle -1. So in this case, instead of updating, we will call the same function, so that in this case the middle +1. So in this case we are ignoring the left half of the array and only sending the right half of the array. So it will again perform the binary search on the right half of the array. So we are calling this recursive binary search with left index as middle -1. We are ignoring the left half. So it will go here and again come with a half of the array. So similarly, if the target is greater, right, so we have to ignore the right half. In that case, we will be updating this right index as middle -1. So let's run this and see whether this recursive approach works or not. So yes, I want to perform binary search. Let's search for 38 in the array. You can see here it is giving the same result as the iterative approach. But in this case, what extra is happening is, so for every function call, internally it has to keep track of the stack. So it has to keep track of every call and remove every call from the stack and return the results. So that is the extra process in the recursive binary search. So let's see the time and space complexity of binary search. So as I said, in every iteration, we will reduce half of the size of the array. So we can construct the time complexity equation like T of n is equal to T of n by 2 plus 1. So if we solve for this equation, we will be getting the time complexity of binary search as big O of log n to base 2. So the space complexity for the iterative approach, it is big O of 1. So for the recursive approach, we need extra space for the stack, right? So for every recursive call, we need to store the stack. So in that case, it will be big O of log n. We have seen how to find the target element in a sorted array using both iterative and recursive approach of binary search. So if we compare both the method, right, the time complexity for both the method remains the same, big O of log n to base 2. But when it comes to space complexity, the recursive approach requires extra space for the stack. So it comes down to the space complexity of big O of log n. So I'll be sharing the link to this notebook in the description. You can go through it. So until then, keep learning, keep teaching, and keep sharing. Thank you. Let's meet in the next tutorial. Please like, share, and subscribe to my channel